G'day, my name is Yevgeny Stadnik. I'm currently working at the University of Sydney in Australia, and today I'd like to discuss some of the ways we can use precision tabletop experiments to search for ultralight scalar dark matter. So the motivation for my research is to help identify the nature and microscopic properties of the dark matter. And so if we go back several decades or so ago, the majority of experimental efforts, initially in terms of direct searches for dark matter, have been focused on so-called weakly interactive massive particles, or WIMPs for short. And these particles live in this canonical mass range from about the rest mass of a proton or the hydrogen atom, and going up to several times the masses of the heaviest atoms that are known to us. So in this case, because the number density of particles is quite small for the observed energy density of dark matter, we expect to see particle-like signatures of these WIMPs in this case. So for example, if a WIMP, flux of WIMPs is incident onto a detector containing an array of target atoms, these WIMPs can scatter off, for example, atomic nuclei and deposit energy onto the nuclei, which would cause nuclear recoils and emit scintillation light, or this can also ionize, for example, the atomic electrons as well. On the other hand, in recent years, there's also been growing interest to search for alternative dark matter candidates. And one of the interesting possibilities is that the dark matter may consist of bosonic particles with very small masses that live in this green region over here. So the mass range here is complementary to WIMPs, where we go anywhere from as high as about 1 electron volt, which comes from the requirement of having a large number of particles per de Broglie volume. So we have a classical field in this case. And we can go all the way down to particle masses of the order of about 10 to minus 21 electron volts, where the de Broglie wavelength becomes quite large in an astronomical sense. So because the number density of particles is very large here, we essentially expect there to be these undulating field-like patterns emerging in the dark matter field, where if we look at some small region of space over a reasonably small timescale, basically what we see is an oscillating field, a classical field, where the frequency of oscillation is determined by the mass of the dark matter particle, and the amplitude of oscillations at this point will be inversely proportional to the mass of the particle and proportional to the square root of how much these low mass particles contribute to the dark matter density in this case. So this is the dependence for the usual underdamped harmonic oscillator, which is the simplest form of potential we can have for one of these low mass dark matter fields. Now the oscillations here will not be perfectly coherent because of the fact that in our galaxy there is a non-zero spread in the kinetic energies carried by these dark matter particles. And this characteristic spread in kinetic energies is at the level of about 1 part per million relative to the rest mass energy of the dark matter particle. So what this implies is that there should be a finite coherence time, which is approximately given by a million periods of oscillation here. So for all intents and purposes, we can treat the oscillations of the field here as nearly monochromatic. So what is interesting about these bosonic dark matter fields is that there are a number of interesting wave-like signatures we can search for, and the exact signatures will depend on the type of boson that we deal with and the types of interactions that these bosons may have with ordinary matter. So in this talk, I'm focusing only on spinless dark matter. We can, of course, also have spin 1 dark matter fields and spin 2. But if we consider only spin 0 fields, there are 2 broad possibilities according to the parity assignment of the fields. So on the one hand, we can have pseudoscalar types of particles like axions, where the underlying field has an odd parity assignment. But we can also have scalar types of fields where there's an even parity assignment. So this difference in the sign here can lead to significantly different experimental signatures. So pseudoscalars can induce time-varying electric dipole moments and spin precession effects, while scalar dark matter can induce apparent spatial temporal variations of the so-called fundamental constants of nature. So what is interesting about these 2 particular types of effects is that the signatures here scale to the first power in an underlying interaction constant. This is because we can have effects like time-varying energy shifts, phase shifts, as well as accelerations or torques exerted on bodies. And these first power effects are quite different from traditional signatures of dark matter, which have a second or fourth power scaling in the interaction constant. So traditional effects of dark matter involve searching for effects like collisions, absorption, or interconversion of ordinary matter with dark matter. But because the interaction constants that we deal with are inferred to be very small parameters, having a first power signature in this case can in principle lead to a very big advantage in terms of the experimental reach of these types of approaches. And so what I'd like to do today is discuss the possibility of scalar dark matter, how scalar dark matter can induce apparent variations of fundamental constants, and some of the predominantly laboratory and tabletop scale techniques that we can utilize to search for this type of dark matter. So one of the simplest ways in which dark matter may induce apparent variations of the fundamental constant of nature is if we have, for example, a linear interaction of an oscillating scalar field phi with the electromagnetic field tensor F of the standard model. So in this case, there would be apparent oscillations in the value of the fine structure constant alpha, where the frequency of oscillation is determined by the mass of the dark matter particle. Now, the size of the oscillation alpha here is proportional to the local amplitude of the scalar field phi naught, and also the amplitude of oscillations alpha here are inversely proportional to the new physics energy scale lambda, which appears in the denominator of our non-renormalizable operator here. We can analogously consider the interaction of an oscillating scalar field phi with some standard model fermion, in which case we would expect to see apparent oscillations in the values of the fermion masses in this case. And the difference here is that our new physics energy scale lambda can in principle be different, or in principle also unrelated to the new physics energy scale for the scalar photon coupling above. So apart from these so-called linear phi interactions, we can also have analogous quadratic phi interactions, which may potentially arise if our model has some underlying Z2 symmetry, which would preclude odd powers of the scalar field appearing in the interactions that we write down. So with phi-squared interactions, we have the same types of oscillating time variations and fundamental constants as we had above, except in this case, the phenomenology for phi-squared couplings turns out to be richer, because in this case, we have, first of all, changes or differences in values of fundamental constants, which are correlated with the change or difference in the local dark matter density. So for example, we understand that over the last 13.8 billion years, the expansion of the universe would have led to a significant dilution of dark matter, going from the earliest few minutes of the universe to the present day. And so over this long cosmological time window, we'd expect there to be differences in the values of fundamental constants, which are correlated with this enormous change in the dark matter density. Another interesting feature of scalar dark matter field models with phi-squared interactions is that they predict that the effective scalar particle mass will be shifted from its bare value in the presence of a non-zero ordinary matter density here. So for example, if the scalar particle mass were to increase inside of matter, we would have screening of the scalar field in and around the region of matter in this case. So this is quite similar to how we have, for example, screening of magnetic fields inside of superconductors. So let's take a look at the comparison between linear and quadratic couplings in a little more detail, since we already mentioned screening here. And so let's have a look at effects when we're sitting quite close to a massive body, like, for example, Earth. So if we look at a linear phi coupling here, the classical equation motion is the usual Klein-Gordon equation, where we have the source term in pink. So if we solve for the scalar field profile outside of a massive spherical body, we find that we will have a linear superposition of two terms. The first term is the oscillating time function, which corresponds to the dark matter component. And the second term here is a Yukawa type term, which is associated with the exchange or generation of a scalar field by a source body at one point, which can then be filled by a test body at another location. So this is a relatively straightforward linear combination. But what is perhaps less obvious is what happens in the case of quadratic and phi interactions. In this case, in the classical theory, instead of having a source term in the equation of motion, we instead have an effective mass term in orange here. So what this means is that we can't simply exchange a scalar boson between two bodies in vacuum. In other words, there are no purely classical sources in this case for a phi-squared theory. But what does happen is that the effective scalar particle mass is shifted away from its bare value in the presence of a non-zero matter density and this phi-squared interaction with the dark matter field. So if we solve for the scalar field profile outside of a spherical body, in a purely classical theory. But in this case, we see that the solution is an oscillating time function, which coincides with the dark matter component. But now the difference compared with the linear phi case is that now the amplitude of oscillation explicitly depends on how far away from the center of this body we find ourselves. So depending on the sign of the phi-squared interaction that we start off with, it's possible to have either amplification or screening of the dark matter density when we're close to the surface of this massive body. Now, if we depart from the classical theory in this case, then what we notice is that for a phi-squared interaction, it is possible to exchange a pair of scalar bosons simultaneously between two bodies. And so this exchange of two scalar bosons leads to this modified Yukawa type contribution, which falls over the distance like 1 and r to the third power. And this here is an explicitly quantum contribution because we have 1 power of Planck's constant entering the numerator in this case. So just to elaborate on the point of screen and anti-screening for quadratic couplings, what is important or can be important is the role of the boundary conditions when we consider this problem here. So here is our classical Klein-Gordon equation again. So basically there are two possible choices for the boundary conditions. So the first choice, which is the one which was studied initially, is that we can assume that the momentum of the scalar dark matter field is exactly zero if we go sufficiently far away from the body. So in this case, what we conclude is that there's generically screening if we consider the negative sign phi-square coupling. And if we consider the plus sign coupling here, then there's amplification or anti-screening of the dark matter field in the vicinity of this massive body. Now, what we have to note is that for the scalar dark matter field in the galactic dark matter halo, the momentum of the dark matter field, even as we go very far away from the surface of the body, is never strictly zero. It can be very small and non-relativistic, but technically non-zero. So if we allow for the possibility that the momentum is non-zero and finite away from far away from this massive body, then we can choose a different set of boundary conditions, which has been the topic of a number of investigations in recent years. And the conclusion in this case is that for the negative sign coupling, we again generically have screening, just like as we did in the case of the first boundary condition choice. And if we consider the positive sign for phi-squared interactions, it is possible to have amplification in this case, but only if we are on resonance or very close to resonance in this case. In other words, if we consider the dark matter waves as scattering off of this massive body, then in this case, the amplification or strong amplification only occurs at or near the poles of the scattering or S matrix in this case. So let's talk about some of the ways in which we can probe oscillations in the values of fundamental constants. There are a number of techniques which are tabletop scale in nature. And so some of the techniques which have been proposed and in many cases implemented include atomic spectroscopy as well as clock-based methods. So these can span a very broad range of possible masses in the red region here. We can also use cavities to cover a similarly broad range of masses in the yellow region here. And what is quite exciting is that it's possible to often combine these two approaches together in a hybrid style of experiment. In the mid-band mass range, we can utilize atom interferometers in the green region here, and there are a number of proposals and developments on this front. And then finally, at the highest masses, optical interferometers can be used as powerful probes in the blue region here. So let's start off at the lowest possible dark matter masses, where we deal with periods of oscillation which are of the order of a month or shorter than that. So in this case, a very powerful class of techniques involves atomic spectroscopy approaches, where the basic idea is that if we have a pair of transitions between two different pairs of atomic energy levels, then in this case, if we measure the ratio of these two transition frequencies with respect to one another over time, if there are oscillations in the values of fundamental constants induced by an oscillating dark matter field at some particular or characteristic frequency, we would expect to see oscillations about the mean value of the transition frequency ratio in this case. And the frequency of the signal that we will search for or hope to find in this case will be proportional to the dark matter particle mass in this case. And we expect to see these oscillations in the frequency ratio measurements as long as the two transitions that we use have different sensitivities or responses to changes in the values of the fundamental constants. So this approach has been utilized by a growing number of groups around the world. This is mainly work which has been done by a group at metrological institutes in Europe, the US, and also in Japan. So the first set of data that we used to do this were actually unatomic radio frequency transitions, which are not used as metrological clocks, but then people have used a number of microwave clocks, and especially also optical clocks in this case. And recently, I made a proposal that it's possible to utilize exotic atoms and their spectroscopy measurements to also search for example, the interaction of the scale dark matter field to muons by using data, for example, in atomic muonium, as well as a number of different muonic atoms. So if we go to higher dark matter particle masses where the frequencies of oscillation become faster, then we can start to utilize techniques which haven't traditionally been considered when it comes to searches for variations of fundamental constants. So one of these approaches is based around the use of solid materials or cavities here, where the basic idea is that the length of the solid is proportional to the atomic Bohr radius in the non-relativistic limit. So if we define a reference frequency based on the length of the solid material, we see that we'll be sensitive to a change in alpha and the electron mass, provided that the changes in these fundamental constants occur sufficiently slowly in order for the length of this object to be able to respond fully to the changes in the atomic length scale in this case. So we can take this solid cavity-based frequency on the left here and compare this against an atomic transition frequency. So if we consider an archetypal electronic transition frequency between different Rydberg levels, in this case, the atomic transition frequency scales proportionally to the Rydberg constant in the non-relativistic limit. So we see that there's an extra power of alpha as compared with the cavity-based frequency on the left here. So already in the non-relativistic approximation, we see that a comparison of an atomic transition frequency to a solid cavity-based frequency is going to be sensitive to changes in the value of alpha here. So this approach has been utilized by a growing number of groups around the world now, and about a dozen different clock cavity combinations have been used. Some of these searches, for example, the one in mines, have been performed in multiple iterations now. So we can also go down a different path where we keep the solid cavity from before on the left, and now compare this against a different type of cavity, which consists of a pair of freely suspended mirrors here. So the idea here is that in this case, if we mount the pendula if we mount the mirrors here on double pendular suspension systems, then for dark matter frequencies of oscillation lie above the natural frequencies of the mirror suspensions. In this case, the length of the second type of cavity would be basically unresponsive to changes in the values of fundamental constants. So in other words, the second type of cavity provides us with an excellent reference frequency cavity, which is basically insensitive to the effects of the more rapidly oscillating dark matter field in this case. So by comparing these two different cavity-based frequencies against one another, we see that we'd be sensitive not only to oscillations in the value of alpha, like we were in the atom to solid cavity comparison from the previous slide, but in this case, we would also be sensitive to oscillations in the value of the electron mass here. So the way in which we do these types of comparisons is important in terms of determining which specific physical parameters our experiments are going to be sensitive to. And the first results of a related small-scale cavity-to-cavity comparison experiment have recently been reported by a group of researchers at Northwestern University in the US. So we can actually take this cavity-based idea and already apply this in large-scale instruments, which are used for the purpose of gravitational wave detection. So the basic idea is that the interferometer has two arms of approximately the same length here, and if there are changes in the values of fundamental constants, then this will, for example, induce oscillations in the thickness of the beam splitter in the middle of the interferometer in this case. So at some particular moment in time, our main reflecting surface can be shifted towards the top left, and so our reflection point will be shifted towards the left in this case. At this moment in time, we see that the length of the horizontal arm will be slightly longer than compared with the length of the vertical arm. So in this case, by measuring changes in a differential arm length in this case, we're going to be sensitive not only to oscillations in the thickness of the beam splitter, we're also going to be sensitive to oscillations in the refractive index of this beam splitter material as well. And so the first results using this particular approach have been reported using a number of data sets. Firstly, this was done using data from the G600 apparatus. It's a 600-meter detector in Germany. Then this has also been done using data from the smaller 40-meter scale Thermalab holometer in the US. and most recently also using data from the third observing run of LIGO as well. So thank you very much for watching.